Hi everyone, my name is Jawad Gull and I'm lead bridge engineer at WSP Lincoln, Nebraska office. I have about 17 years of experience in bridge analysis, design, detailing, research, and teaching. And today I'm going to briefly talk about bridges. Bridge is a structure built to span a physical obstacle such as road, railroad, or a body of water without blocking the way underneath the bridge. Another term that is used for bridges is viaduct. And a viaduct is a specific type of bridge consisting of series of arches, piers, or columns carrying a long elevated road or railroad. Here is the famous Millau Viaduct located in Millau, France. As you can see, it's a very long bridge supported over series of piers or columns. In the USA, there are approximately 610,000 highway bridges, and 40% of the bridges are 50 years or older. These statistics highlight the importance of bridge engineering and demand of bridge engineers in the USA. How many bridges you have in your country? Please post in the comment section below. Next, I like to go over components of a typical bridge. Starting from the top, bridge parapet prevents the vehicle from falling over the bridge in case of an accident. The bridge deck provides the riding surface to the vehicles and is often supported by large beams called girders. Girders sit over devices called bearings and are supported by the bridge supports. The distance between the two supports is called bridge span. This particular bridge has 3 spans and 4 supports. There are 2 types of supports. The end supports are called abutments, and the intermediate supports are called piers or bends. A bend typically consists of a bent beam, column, footing, and piles. There are a lot of different types of bridges, but I'll briefly talk about the bridges listed over here. And these are slab bridges, concrete pre-stressed girder bridges, steel eye girder bridges, segmental bridges, cable stayed bridges, and suspension bridges. Slab bridges have bridge slabs or decks supported directly over the bridge supports that are piers or abutments. These bridges do not have girders supporting the bridge deck. These bridges can span up to 35 foot with a single span or up to 50 foot with continuity or multiple spans. In concrete pre-stress girder bridges, the deck is supported over concrete pre-stressed beams. Concrete pre-stressed beams often have an eye section containing steel strands that were stressed before casting of concrete. These bridges can span up to 200 feet. Next, we have steel eye girder bridges in which bridge deck is supported over steel eye girder. As you can see in the photo over here, the cross section of steel eye girder looks like letter I and is fabricated by joining the steel plates together. These bridges can span up to 300 feet using normal or 50 KSI steel. They can span up to 500 feet using high performance or 100 KSI steel. Next, we got segmental bridges that are built by joining the prefabricated bridge segments together. These prefabricated bridge segments are often joined using post-tension tendons. These bridges can span up to 600 feet. Next, we have cable-stayed bridges in which bridge deck is supported by cables tied to a large column or pylon. These bridges can span up to 2,000 feet. This particular bridge shown in the photo here is Guadiana International Bridge at Portugal and Spain border. Next we have suspension bridge. In suspension bridge, the deck is supported by large suspension cables that are connected to the bridge deck by a series of vertical ties. The suspension cable is supported over bridge pylons and anchored into bridge abutments. These bridges can span up to 7,000 feet. The bridge shown in this photo is Akashi Kaiko Bridge, located in Kobe, Japan. Next, I like to briefly talk about bridge cost. Bridge cost depends on a lot of different factors, such as material and labor, complexity of the project, geometry of the bridge, method of construction, and inflation, to name few. With that said, the bridge cost shown in the table below is the approximate ballpark cost of different types of bridges as of 2023. So slab bridges cost approximately $180 per square foot. Concrete pre-stressed girder bridges cost approximately $150 per square foot. Steel I-girder bridges cost approximately $200 per square foot. Segmental bridges cost approximately $300 per square foot. And cable stayed and suspension bridges can cost anywhere between $1,000 per square foot to $3,000 per square foot. How much a typical bridge cost in your country? Please post in the comment section below. Please do not forget to mention the type of the bridge. Next, I will talk about bridge design loads. There are a lot of different loads that bridges are designed for. I will talk about only few common bridge design loads that are listed over here. And these are dead loads, live loads, wind loads, thermal loads, fatigue loads, and vehicular impact loads. Dead loads typically consist of weight of the bridge components. The bridges are designed to carry their self-weight, in addition to the weight of the vehicles traveling over them. If bridges are not designed properly, they can fail under their own weight. This photo shows the lateral torsional buckling failure of an I-girder bridge located in Edmonton, Canada. This failure happened in 2015 and the bridge was supported under its self-weight. These photos here shows the collapse of the Marcy pedestrian bridge in New York. The collapse happened in 2008 during the deck pour. Live loads consist of vehicles traveling over the bridges. There are a lot of different types of vehicles that use the bridge. However, we design the bridges for an imaginary live load that can envelop the force effects of the common vehicles that uses the bridge. This imaginary live load does not take into account the heavier vehicles that need permits to go over the bridge. In the permit process, the weight of a heavy vehicle is given to the bridge engineer, who then analyzes the bridge and makes sure it's safe for the vehicle to use the bridge. Failure to obtain the permits for a heavier vehicle can result in the bridge collapse due to vehicular load, as shown in the photo here. Wind loads is another load that is considered for the design of bridges. It becomes very important for certain type of bridges. The short clip shown here shows the collapse of Yokohama Narrow Bridge due to wind-induced vibrations. The Yokohama Narrow Bridge was located near Seattle in the state of Washington. It was open to traffic on July of 1940, and the bridge collapsed 4 months later in November 1940 due to wind-induced vibrations. Bridges are also designed for thermal loads and thermal movements. Typically, a bridge is designed to freely expand or contract due to temperature changes. If this movement is somehow constrained, it can damage the bridge components, as it happened for this 3-span continuous steel eye girder bridge located in Kansas City, Kansas. The bridge was built in 1974 and had only one of the piers fixed and rest of the supports as expansion. This allowed the thermal expansion of the bridge happening on both east and west abutment. In 2005, the bridge was repaired and the east abutment of the bridge was fixed. With this abutment fixed and having more stiffness than the pier, all the thermal movement was pushed toward the east abutment. And due to this excessive thermal movement, the bearings were pushed to their limits, the girders were ramming into the back wall, and there were damages in the abutment cap beam. Fatigue loads are especially important for steel bridges. As steel becomes brittle due to cyclic loading induced from the vehicles passing over the bridge, the brittle steel tends to crack, as shown in the photo on the left. The excessive cracking or cracking of a critical component of the bridge can result into the collapse of the bridge, as shown in the photo on the right. Vehicular collisions are also considered in the bridge design. If the bridge component is not adequate to take the force of a vehicular collision, it can cause the collapse of the bridge. As shown on the photo on the left side, this bridge pier collapsed due to the impact of a heavy vehicle, resulting in the collapse of the bridge. And the photo on the right side shows the collapse of Queen Isabella Causeway Bridge in Texas in 2020 when it was struck by a barge. I like to further highlight the importance of bridge engineering by discussing a couple of bridge collapses. The bridge engineers have to be very diligent in bridge design, bridge construction, and bridge inspection. Otherwise, it can cost lives. The I-35 West Mississippi River Bridge in Minneapolis, Minnesota was built in 1964. It collapsed in 2007 at the age of 43 years, causing death of 13 people. And a pedestrian bridge near Florida International University, Miami, Florida, collapsed in 2018 during its construction, and it caused death of 6 people. Next, I like to talk about the research and development in the field of bridge engineering. There are a lot of different topics of research in bridge planning, design, analysis, detailing, fabrication, construction. I'll briefly talk about the topics that are listed over here. And these are the development of ultra-high performance concrete materials, techniques to extend the service life of the bridge, structural health monitoring, and accelerated bridge construction. Ultra-high performance concrete consists of cement, sand, admixture, and steel fibers. Ultra-high performance concrete, or UHPC, has significantly higher strength compared to a regular concrete, and it is often used to join the prefabricated bridge components. There are a lot of techniques that are used to extend the service life of the bridge. The bridges are generally designed to last for 75 years. These techniques are aimed to extend the service life of the bridge to 100 years or more. The technique shown on the photo over here is called the spray applied liquid membrane, that is aimed to prevent the intrusion of water into the deck, resulting in its deterioration reducing the service life of the bridge. Structural health monitoring is aimed toward finding the location and extent of the damage by looking at the vibration characteristics of the bridge. In structural health monitoring, different sensors such as accelerometers and strain gauges are attached to the bridge. The data from these sensors is analyzed to determine the vibration characteristics such as natural frequency and damping ratios. The change in these vibration characteristics over the period of time is used to determine the location and extent of the damage in the bridge. Accelerated bridge construction, as the name indicates, is aimed toward decreasing the construction time of the bridge. There are a lot of different techniques that can be used to decrease the construction time of the bridge. I'll talk about a couple of techniques that are listed over here. That is the use of self-propelled modular transporter, commonly known as SPMTs, and the lateral slides. Accelerated bridge construction using SPMT involves the construction of the bridge off-site and then bringing that bridge to the site using SPMT for replacement or construction. This photo here shows PennDOT first SPMT move that was completed in 2019. Here is another example of accelerated bridge construction using SPMT in Connecticut. This bridge was completed in 2019. Decreasing the construction time by lateral bridge slides involves the construction of the new bridge off the alignment, followed by demolition of existing bridge that needs to be replaced, and sliding the new bridge into the place of an existing bridge. This short clip shows the accelerated bridge construction in Massachusetts using lateral slide. The traffic was only closed for 10 hours for this bridge replacement project. And with that, thank you for your time. Please post your questions and comments in the comment section below. Please like and subscribe to get notification on newly posted videos. Thank you.